the function power of time. When we determine p prime of t, is the same with determining dp differentiated with respect to t. This is called the Leibniz notation. It means the same thing. So what does this represent? It's still the rate of change of power with respect to time. With respect to time. What will be the measurement unit? A double measurement unit. So let's look and see in this problem. They are not giving us measurement units. I don't know, kilowatts or watts per year. I'm not sure. I'm just gonna write something. I'm assuming kilowatts per year. But since it's a ratio, it has to have two measurement units, one coming from the top, one coming from the denominator. Okay, part B. Interpret the statement dp over dt as t equals 2 equals 3.5. Perfect. So when we use this notation, it's very easy to ask, find p prime of 2. And that's all it means. When we use the Leibniz notation, we use a vertical bar and we write what we're asking to be replaced by. So t in this case, we want it to be replaced by 2. So we want the same thing with p prime of 2. But if we use this notation, we use a bar, a vertical bar, and then t equals 2. So now they should put the measurement unit here. They didn't. Oh, I'm sorry, I forgot to stop sharing. Sorry about that. Okay, so these are the same. So dp over dt is the derivative evaluated when time is 2 years. 2 years since 2020, January 1st. So what does this represent? Is the rate of change, so it's positive rate, so it's increasing. The rate of change of power with respect to time in the year 2022. 2 years later, from the moment they started looking at this. So the rate of change, so it's increasing at a rate of 3.5. I'm not sure what the measurement unit is, but I'm saying kilowatts per year, and that is in 2022. So now, since we picked that, I'm curious to see how, if did they write any measurement unit here? Okay, percentage points. Okay, but it didn't. Oh, my bad. Represents the percentage. Okay, my bad. So this is percent per year. Sorry about that. So then this is in 3.5% per year. I should have read it more carefully. Sorry about that. Okay, and what did they say here? Okay, percent of is increasing at a rate of, okay, fine. Good. So let's go back. If you want to choose again, I think we're already tired of all this. We just did all of different problems and radicals and rational functions as well as quadratic. So what I recommend at this point is let's graph another, choose another function and graph which is going to be an approximation of the derivative. So choose any of these graphs, and that will be the end of chapter 2. And then we'll talk about our test. So please choose any function from here that you would like to graph its derivative.
Number 6.
Number 6. Perfect. Number 6 is good. So let me graph number 6. Please make sure you have enough room underneath, right underneath, perfectly one under the other. Okay, so let me copy something like, obviously it's a nice symmetric curve. It's with odd with respect to the origin, symmetric with respect to the origin. So it does this and then crosses and goes down and does this. Okay. Good pick. Okay. So this is our function f of x, and we want to be able to sketch an approximate. This is not going to be exact, but an approximate graph for f prime. Okay. So I'm going to have to draw some tangents, right? So first of all, I start with what is easy. At this point, the derivative must be 0. Sorry about that. Okay. Also at this point, the derivative must be 0. How come? That's the slope. The slope here is 0. The slope here is 0. So this is what I'm graphing. I'm graphing the slope, which is the rate of change of this function, at every point. Okay. So obviously here is negative. I'm going to have to estimate. I'm going to say it looks like negative 1. 1 over 1. Okay, where else is negative? So obviously the slope here is positive, positive, positive. So all this piece has to be above the x-axis. This piece, that will be above the x-axis. Between this point and this point, these two, it's all decreasing. So the function is decreasing, which means the derivative has to be has to be negative under the x-axis. Now it's again positive. Okay, so this is tiny positive, almost 0, almost 0. Then it's increasing till a certain point where it appears to be the steepest. So here at this point, I'm going to say it's a maximum here. Maximum increase. So how much? I don't know. 3 over 1, 2 over 1, 2 over 2. Very difficult. But I know that this is the maximum. I cannot estimate. 1 over 1, if you want to say 1, if you want to say 2 over 1, you can go to 2. I don't know. But obviously this is the highest. This is low, increasing, 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 decreasing, decreasing, decreasing towards 0. So this slope here and this slope are definitely, this is closer to 0 and this is much higher. And then all of a sudden it gets to smoothen out till 0. So I will say something like this. Okay. Now it's all negative. So negative, 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 but closer to 0. And then it has to have the same outlook on this side. How come? Because again, it has to come to 0. It has a maximum somewhere here, and it has to get closer to 0. So this is the graph, very, very approximate graph of f prime. But the shape is good. The symmetry is still there. Obviously, between these 2 points, the function is decreasing, which that means the derivative has to be negative. Here, it's increasing till a point and then starts leveling off to a point and then leveling off, but also always positive because the slope is positive. Here, the slope is positive towards 0. So this is the graph of f prime, and these are the points where it has a maximum. Here's the point where it has 0. Here's the point where it's the maximum negative. Here's the point where it has 0, slope 0. Here's another point where it has a positive maximum for the rate of change. This, for any point here, this height represents the rate of change. So here is maximum. I don't know what it is. Could be 1, it could be 2. So that's how we look at graphing, given a function, graphing an estimate of the graph of its derivative.